Hello everybody, this video is about support vector regression in Jupyter Notebook. So we need to load the data, loading the data set. To load the data we need to import pandas library. So we import pandas as PD. Then we read the data. Set. I call the object my data equal. So my data is the object here to read my data. So pd.read underscore csv parenthesis quote. The data is found in this folder. So the lake here, Microsoft Excel, comma separated value. I copy the directory, and the data itself is here. The content have time ET. So it is evapotranspiration, SH is specific humidity. Here we have air temperature, you have soil temperature, you have precipitation, you have soil moisture, and you have lake level. So I paste here double backslashes lake dot csv, double these two backslashes as well, and I run. So my data is already read, so we need to see the statistics. Type describe, and we are going to take level as our output variable. Our feature and the 6 other here are the input features. If you want to see the correlation coefficient between the features, type mydata.core. So here have the correlation coefficients. We now need to prepare our input and the output features. Here the input feature first, let's see. Our predictor, so x equal, from the data set we not need to drop lake level, and need also to drop time. Time doesn't appear here because it has characters, is date, so you cannot have the information about it here because it's not numerical, but we need to drop it. My data dot drop, so we drop time, as well as lake level. So x is equal to 1. Sorry about that. T lake level dropped from the data set to have our input features. So we go to x.shape. We see that we have 240 observations and 6 variables. So let's go and prepare our output feature. Let's go y is lake level. So we take lake level from the data set to have our y. So y dot shape. This way to get only lake level and 240 observations. So the next step is to split the data set into training and the testing data set. To do this, we need the function train test split function. We need to import train test split function. So from scikit-learn dot model underscore selection import train test split. Then we split the data. Here we have x train, x test, y train, y test equal train underscore test underscore split. We split x, we split y. We have the test size. I put here, let's say 20%, 0.2, and then the random state equal 30. So this code, we already split our data, so let's print the shapes of our respective data sets. So x train dot shape, x test dot shape, y train dot shape, y test dot shape. So this code is going to output all we need, or all there is as a number of observations and variable within each of these data sets. So we have this x train, x test 48 and 6, y train 192 for lake level only in the training data, and the 48 observation in the testing data. So you move to the next step. We already are going to next step. Next step is because you already have everything you need to run the support vector regression model. So we go to support vector regression. For this, we need to import SVR from the scikit-learn.smv. Scikit-learn.support vector model import support vector regression. So we now need to create the support vector regression and fit it. creating and defeating the SVR model. So our output is variable is lake level, so I call the model lake level underscore SVR equal SVR. Then this is the model creation, then we fit like the SVR regressor. The first part is the SVR regressor here. Then we fit it on dot fit on X train Y train. There are some arguments you want. If you want, I put everything by default here. You can put your epsilon equal 0.epsilon2. Normally by default is 1. You can put the kernel as you want, RBF or whatever you want, but I leave everything by default here within the regressor. So just take the regressor and I fit the model. So let me print the coefficient of determination, printing the R square, the model. So print the R square this is a training model. We are going to take 2 decimals. So this is going to be the lake level underscore SVR dot score. We need the score, and the score is on X train, Y train. So 28%. The training model R square is 28%. So let's evaluate our training model. To evaluate the training model, we need to import from scikit-learn.metrics import. We need the mean square error, mean absolute error. Of course, the mean square error also. We are going to have also our R2 score and explained variance score. Mean absolute error, mean square error, the R2 score, explained variance score. Okay, the idea is to fit on the training data and the predict on the testing data. So normally we should not predict on the training data, but I am going purposely to also fit on the training data in order to have my matrix here, mean absolute error, the R2 score, the explained variance error, and all I need to compare with the training, with the testing data as well as the cost validation, because the purpose is to compare the cost validation score on testing, on training and testing. But I would like also to have mean absolute error, and the variance, the explained variance error. And for this, I need to fit on the training data. So let's say I need to predict on the training data. Predicting on the training data is just for comparison purposes. So let's call it train right equal late level SVR dot predict X train predict. So we are going to, let's use another way to print our R square on the training data. So the same way we already know that it's 0.28 using dot score. Now if we use R2 score, it's going to give us the same thing. So the point the R square is decimals again. This time it's R2 score. This function R2 underscore score. It's on Y train and Y train head, and you will see we'll get something 0.28 0.28. So two ways, using LL underscore SVR dot score X train Y train, or using R2 score Y train head, you get the same thing. So the next step is to have our mean absolute error. The mean abbreviate mean absolute error. So print the mean absolute error is decimals again Y train head. So now we have our MSC, and after running the MSC, we are going to compare the MSC obtained from this method of predicting on train, compare it with the MSC from the cross validation. So print is mean squared error Y train train head. Point 15. The RMSE, root mean square error. To this we need to import numpy as np. Because we are going to use numpy np.sqrt, so print np.square root of the mean squared error of y train height. Point 39. Then the spline variance error is also one of the important metrics to have in order to compare the models. The spline variance score, let's call it. That stands for spline variance score. Okay, PSV is stop at 2 decimals. Explained variance underscore explain underscore variance underscore score, and have the score on y train head. Point 30. So now that we have the metrics on our train data, we are going to predict on the testing data and evaluate the model as well. Here let's call y test spread equal break level underscore svr dot predict and so on x test. Let print the first 10 predicted values and see y test print all the rows of the first the first 10 values, predicted values. No. Now we need the coefficient of determination, the R square. we are going to use two different methods here in the C. It's going to give us the same thing, using the R2 score and using point score. So let's have a print using the R2 score. The R square is take decimals. R2 underscore score white spread. As we use here, R2 score 28. We use L underscore dot svr underscore svr dot score. We are going to use this method also, and we compare the values R2 score and dot score. So we are going to print the R square is into F decimals. This time you have like level. These are model dot svr ll underscore svr dot score. The score is on X test and Y test this time. %30%. So either we go from this, the model dot score on XS Y test, or we first predict and then we use R2 score. It's going to give us the same thing. Okay, now we are going to plot the observed and the predicted data. Lake level data, of course. So we need to import mat plot lib dot pyplot as plt. Then we need to set the boundaries of our plots and also some other characteristics. Okay, let's have the figure size. So plt dot rc params, need the parameters. So we take the figure dot fig size, figure dot fig size, okay. So this should be in quote. Figure dot fig size, we put the quotes. So take all figure dot fig size, select all, quote, equal, we take 10 by 6 for instance, set the range x equal, the range is going to go through the length of x test. Then excuse me, we are going now to plot our observed data. So we plot it with x-axis, this x-axis, and the y-axis is going to be our y-test. So the plot here is using the predicted. So the predicted is on y, on test data, and then the label equal observed, and then you have the color, we take K, and then you have the line style, the fill line, we run. So this is the observe. Later, the next code is to plot the predicted level. Plot. We still have our x. This time we call it y test spread. This is predicted, and the label is predicted. And the color, same color, don't change, but we are going to change the line styles. Line style equal to, going to take dash. We run. So here we have the observed, fill line, and the dash here is the predicted. So let's deal with y labels and x labels. PLT.y labels is lake level in meter. And PLT dot x label is the sample, so it's testing sample data. Sorry, I have to put the codes here. So we have a lake level on y axis and a testing sample data on x axis. Let's put the legends. So we have PLT dot legend we have the BB box, boundary box, to anchor equal, let's take 0.5 for x and negative 0.2 for y, two shifts, number where we want the legend to be located, so we are going to put it on lower center of the plot. Then number of columns, we need n col equal to, we need a column for observe, another column for predicted, so we put them side by side. And then frame on, no, we don't want a frame around the legend, so frame on we put false. Invalid syntax. PL2.legend box to anchor. Okay, there is space here, there shouldn't be. Okay, this is the issue. So we have our legend here, observe and predicted. Okay, so we have to finish with plt.show. If you want to remove the grids, so you deal with the grids. So plt.show, it's already shown there. Should be parentheses. Okay, good. So the next step is to plot the prediction errors and the residuals. To do this, you need to go to command prompt, or anaconda prompt, and type pip install yellow brick, because you are going to use yellow brick to plot the prediction errors and the residuals. So the first plot is the prediction errors. You need to import prediction error from yellowbrick.regressor. I already run this command pip install yellowbrick, so that's why I don't get an error warning here. So if you don't do it, it's not going to work because you have to install it. So the next step is to create your visualizer. Visualizer is the prediction error on our model. Our model is lake level SVR. Then the visualizer, you need to fit it on X train, Y train. Come on here. Okay, the error came from the comma I forgot to put. So you need now the visualizer dot score. So you are going to output the scores. The scores are on X test and Y test. You already have the frame of the plot, so now you have the score, and then finally you are going to show it. So visualizer dot poof. So here is the prediction error plot. You have score on test 0.299 means 0.30. So 30%, we took 2 decimals and we got 0.30 their score. So the next step is to have the residual plots. And we are going to do the same thing from yellow brick.regressor. We are going to import the residual plots. Yellow brick.regressor, import residuals plot. Done. You have the visualizer. This residual plot, residual plots, our model SVR. Visualizer equal residual plots L underscore SVR. And we repeat the same thing. We fit on the X train and Y train. Visualizer.fit X train, Y train. Visualizer, residual plots, NLSVR. The next is the score. Visualizer dot score, the score on X test, Y test. Visualizer is not defined. Okay, I'm messing up Z with S. Okay, so we visualizer dot poof to see our scores in the plots. So on training score you have 28, right? And we took 2 decimals, so but here is 3 decimals, so 0.276. And we already saw on testing 0.30, so 2 decimals. Here we have 3 decimals, so 0.299. So we took it to 30, 0.30, 0.28. So if we compare here, R square 0.30, and here R square on training 0.28 with 2 decimals. Very close. So now we are going to evaluate our testing model. So we'll start with the mean absolute error, as we did it before. So the mean absolute error, print take everything to decimals. Mean absolute error y-test spread. .8 on training, on testing, sorry, and you go back to training. The mean absolute error is 0.29. Then we go to the mean square error. And the MSC is .12. I think it was 0.15 on training. Yep, 0.15 and so on. So you continue, you compare the metrics. Now it's going to be the RMSE, the root mean square error. Have NP square root mean squared error, y-test spread. Sorry, there is no underscore here. Let me remove this. 0.35 and so on. We continue with the explained variance score. Explained variance score. And explained variance score is explained variance test predicted from y test. Print. We need T here. I'm sorry about that. Point 30. Let's see on the training, where did we get? It's the same, doesn't change. On training and testing, doesn't change. So the next step is the k-fold cross-validation. This is the most important step here. We are going to take 10-fold cross-validation. So normally we predict on the testing data, then we perform the cross-validation, we compare the metrics, the values obtained. So we need cross-val score here to import from the scikit-learn model selection. Learn.model underscore selection, import cross-val score. So we are going to perform the cross-validation on the testing data, on the training data, then on the testing data. Here we have score on train. This is our object, equal cross-val score. We have lake level SVR, so support for regression on lake level. We have an X train and Y train, and then scoring equal R2. Cross-validation equal 10, the number of folds. So let's have our score on train. This is what we get. So we are going to take the mean of all these. Score print np.min score train. So the mean is 0.15. end of the 10. Here value is 115. Then we go on testing data. Intercept. So score test this time equal cos val score our model. Then on text access my test scoring. Then the number of folds 10. So we have the score test. These are the 10 different values, and then we take the mean of the 10. The mean score on the test. And np.mean of the score test. So the score on the testing is lower than the score on the training, 0.15, 0.12. So this is the end of this video. Thank you very much for watching it. I hope you get something from it in order to help yourself in your research. Once again, thank you for watching.